OK，so shall we start？所以你们如果派你去找一下昊天啊，班长，因为班长，你问他看呀，我觉得怎么说呢？所以我觉得你们的认知对懂还是不懂还是有差，就是你们还不能够认知自己什么都不懂，你们会觉得说我懂很多，其实我要懂或者我要懂很多，其实是不对的。反正你什么都不懂就对了啊，等你才可以慢慢学。如果你一直想要说哦，我要懂这个，我一定要完全懂，我才可以讲。什么叫完全懂？不能完全懂哎。就算提出那个 relativity 的那个人，自己本身提出来的都不懂哎，都不懂啊，怎么会懂哎？哎，是爱因斯坦 reject 黑洞这个答案呢？那答案存在在他的那个 equation 里面啊，还 reject 掉，对啊，是他懂还是他不懂哎？那又是他写出来的理论了，所以他懂还是他不懂？所以你们，所以我们学生就是怎样讲哎，要重新塑造一个懂或不懂的这个东西，你懂对不对？因为他会觉得说，我要懂这个东西，就是他要到他懂。什么叫你懂？就不懂嘛，就是来讨论就对了，然后我们就慢慢懂，这样子，明白吗？就一个一个讨论，一个讨论。所以为什么 FIP 啊，每个礼拜密，每个礼拜密，我又不是 expect 你说，哦，我跟你讲了这个东西，你一定要懂了，你才来见我，不是啊，就是你懂了一个东西，但是你又不太懂，所以我们来 try to figure out 这个 part 到底怎么去更好的理解它，你明白吗？当然，这个是 based on 你要再多读一点东西啊。然后我不是 expect 你读到哦，一定要很会那种。当然，这是最 ideal 的 case 啊，but 不一定会到这个 ideal case 嘛。但 minimum case 是什么？minimum case 就是你多读了一点东西，你来讨论就对了，这是 minimum case，OK 吗？明白吗？Yeah，so 我不知道浩田的 case 是怎样，but、他可以有他的决定选择。我们能帮就尽量帮。OK 啊，Yeah，我觉得 so far FYP 里面，我感觉进展比较好的是小月，就是他每个礼拜都会来跟你说一些新的东西，他懂的东西，他也有不懂的东西肯定，但是我们就可以 build 我们这些不懂的东西哦。我可以可能给他一点 info，或者叫他再去看一点这个东西，然后可能他看新的东西，他懂可能就是88线，对吧？然后可能我再帮他补一点18线这样子，你明白吗？你不要好像来，你一进来你就觉得说，我一定要给提升100%，这个是很 ideal 的 case，but 我希望你们做到 minimum 的 case，对不对？就是你可能有30-40%啊，慢慢我就可以补你到50%，然后你就慢慢进步30、40、50、60这样慢慢来，这样子进步来给我看，你明白吗？因为我们被 train 到考试嘛，我一定要考 pass 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 或者 A，一定要 hit 到那个 target，没有的。我们现在重要的是注意你到底有没有比之前更好，读更好，理解的更快，这样子，OK 吗？如果你一直全部把东西 keep 住自己，我只给 K 先看180的东西，then 怎样呢？那你那些做不来的东西，我怎样建议你呢？还是你做不来就是做不来啊？有人这样子决定，他做不来就是做不来，他不要做了，他就是这是你的选择啦。我是想啊，然后你就没有在学东西啊，因为你就是跟着你自己会还是不会去做嘛。那你要知道哦，你不会的东西是很多的哦。那所以我要给你的一个能力，就是你要把不会的东西变会。管你是在什么 field 里面，不是在数学里面也可以，在不同的领域里面都可以适用的这个 technique，这个 skill，OK 吗？呀呀，所以100分的考卷，我是很难知道你到底有什么问题的咯。 那如果你是一个50分的考卷，我就知道你有什么问题了，因为你这个不会那个不会嘛。那100分我不知道你怎么不会哦，你好像很会这样哦。你知道什么？你知道什么意思吗？所以为什么我们很少出这种给人家100分的考卷或者很容易的考卷，就是因为我不能知道你会什么不会什么，你知道？那如果我考一个比较有挑战性的，OK，我要考你这个啊，你漏掉这个 skill 啊，你这个就不会咯，你明白吗？你 understand 吗？不是说我们什么要简单一点、难一点什么，就是我们是希望你能够去注意你自己的弱点啊，进步你的弱点。但是往往在这个戏里面，就是自尊心太强，你一直攻击他的弱点，他会觉得这么你一直无聊，我吃饱没有事做，对吧？就他就是他自尊心太强，他不能够被你讲他不会的。我就老实跟你讲，我就是不会，我什么都不会啊，我什么都不会。一个 professor 什么都不会，一个 doctor 什么都不会，可以吗？是不是？真的，我什么都不会，我会什么？对吧？是不是？所以你也不用太在意自己，就是好像很挫败这样呀。你就要好好学，好好进步，就 OK 啊。这就是你已经变成一个更好的自己了，对吗？你们有没有对世界的看法有没有变化？现在我想问一下，我就明白了问了，对世界的看法有没有变化啊？你骗我什么？啊，就是你看一件事情，你以前看它是这样，你现在看它不一样，有没有不一样？有哈，晋升有，晋升奖开始有。OK，这是另外一个东西啊，就是说你以前对这件事的看法是这样，然后后来你重新又看到它的时候，诶，好像我有不一样的看见了这件事情。什么叫过后？呀，没有，我不是讲课程的东西，我要你看待世界，看待世界，看待关系，看待人。如果没有的话，你确实你只活在多那里面吧。我没有给你看多那，多那就不见了，你明白吗？我希望你能够 abstract 出这些观念，去到人与人之间，或者你平常的处理事情上面，你有没有转变你的想法？逻辑上啊，还是什么？你明白吗？你要学到这样，这些多那才有用，不然的话就是一堆多那吧，对吗？你要有一个 transferable skill，这个 skill 是可以 transfer 去其他地方。你知道 transferable balance 吗？是吧？他选过，那笔钱是可以转来转去的。如果你用 credit card 的话，你进了你就卡在里面了，转不去。对，要扣10%才可以，是不是？OK，All right. So we'll start the Cohomology. But to start Cohomology, I want to do some motivation for Cohomology. So the motivation will be calculus 2. I want you to remind you on this calculus 2 stuff. Okay. So if you still remember, we define vector field, a conservative vector field, if that vector field is a gradient of a scalar function. What's a gradient of a scalar function? So scalar function is a function from Rn to R. Okay, then the gradient is you take the partial derivative, or take the matrix formed by the partial derivative, and then huh? you yeah, and then you add on it. So so look at this theorem here. So this is a criteria that we teach calculus 2 to check out. So previous class actually was a calculus 2 by Dulip. So I think they should be reaching here already. So suppose that this vector field here defined on an open simply connected domain. So for now, can you relate what is open simply connected now? Yeah, connected. So the simply here is what do we call it in our class? Uh, we don't say simply did we say simply connected? Did we use this term? Yeah. I think we use it. Okay, yeah, simply connected. So the pi1 is 0, right? Okay. And then it's connected. Suppose the f1, f2 has continuous first order partial derivative. Then f is conservative if these two partial derivative is the same. So you partial differentiate the first component with respect to the second coordinate, and then differentiate the second component with respect to the first coordinate. Okay. So the problem here is we don't have problem with if and only if. The problem here is the first condition. You need an open simply connected domain first. You only have this if and only. So the problem is, can you go backward or not? If you have this if only if, does it only apply? Does it imply that your U have to be simply connected? Let me see. Am I saying this right? Okay. So sorry. What I want to say is, if you change this domain here, not open simply connected anymore, does this if and only if still hold? Okay. So what we want to show you is, even if this two partial derivative is the same, it won't be conservative. So meaning it won't be coming from some scalar function. Okay, coming from some scalar function. Actually, this thing a bit related to your complex analysis, I guess. Okay, but anyway, so this is one of it. Later, I will briefly tell you why is it not true. Okay, if pi1 is not 0. And then second is this calculus 2. Do you still remember we proved this using Clairaut's theorem? Curl of a gradient of f is 0. Okay, so this actually constitute derivative differential. Okay, differential of the Durham complex actually. So delta is the first boundary map, and then curl is the second boundary map. Okay, so this is like composed of two differential map is 0. Okay, yeah. Okay, later I will show you. But this is the two things I want you to recall from your calculus 2. Okay, yeah. Okay, let's briefly go through the first case here. So our first case here is actually this. Okay, so if you look at this vector space, sorry, vector field, but your domain, you throw away 0, such that the pi1 is not 0 anymore. Then it's easy to check that their partial derivative is the same. Okay, but there's no f such that partial f with respect to f1 is f1, and then partial f with respect to f2 is f2. Do you recognize this vector field here? This vector field actually is the first rotation. Okay, divided by the length, the norm. It's a rotation. And if you remove the 0 point here, there's no big F that can partial differentiate to this vector field. Why is it the case? Why is it the case? So so actually we can reduce the theorem just now to these star shape subset. Did you guys encounter star shape subset? Okay. So basically you start from one x naught, and then all the line segment to this s naught you will include it. Okay, so that's why you form a star. So as long as you have star shape set, then you will have this conservative condition here. Okay, conservative condition here. So star shape, the pi1 is still 0, right? Pi1 is still 0. Pi1 is still 0. Okay, but might not be is it open? Okay, so in this case it's open, star shape open. Okay. As long as star shape, you can solve it because you can solve these partial this integral here. Okay, so basically you just build your integral on this integrand. So you take your little f1 into f2 multiply by s1 and integrate it. Then this will give your partial derivative condition. Okay, so actually the topology is important to guarantee the solution of that scalar function to your conservative vector field. Okay, but so in this case here, so how to study these things? So we will move to the set of smooth function. Okay, is this what you learn in differential manifold? Smooth function. Do you know that they are the vector space? Vector space, they can add, they can multiply, they can take product. Yeah, so there's a scalar. If can take product, become algebra already. So we just need vector space. So addition. Addition is pointwise. So we can define two operations. So one is taking grad, and then the other is taking curve. This is in MA1 or not? MA2, sorry. Don't have grad. How two only? I thought MA2 is supposedly proving this stuff. Right. Stokes theorem, no. Green's theorem don't have. Don't have. Okay. Never mind, I haven't teach that before, but so you can see that grad is in between C infinity from U to R and then from U to R2 because if your U is coming in R2, then the grad will produce two partial derivative. If curl will combine two functions, become one function. Okay, so you can see that curl and grad is 0, so that means what? We can define, let's say define this new thing called h to the power 1. Okay, previously we put the 1 in the subscript, right? Now we put in the superscript. Okay, so this will motivate the first cohomology. And so we define the first homology of U, first cohomology. So let's call this cohomology because we changed the superscript subscript already. So if it's superscript, we call it cohomology. Then this is the kernel of curl mod out by image of grad. This one okay or not? Because grad and curl define on vector space. So there is a kernel, there's an image. So compose is 0. So we dominate image of grad live inside the kernel of curl, so we can take the quotient. Valid algebraic operation. So far okay. Because it's a subspace, so we can quotient out. Okay, and then what this means here? So this means that if U is star shape, right? Just now we can solve the conservative problems. Meaning what? If we can solve the conservative problem, that means H1U is 0. Meaning because the kernel of this kernel means what? You need to make sure that these things is 0, right? Meaning the partial derivative is 0. Then this function will come from the image of a grad. So meaning what? Kernel of curl equal to image of grad. So the homology is 0. First cohomology is 0 for star shape. Obviously for the open simply connected also 0. Yes, sir. Huh? Why? No need to know first. Let's call it, just call it first. Yeah, no need to know why is it first. Yeah. Obviously, if there's the first, there's a second one. Later we will see. Okay. So this is the first case, okay? Makes sense. So you see, at this, if we call this first, right, then this first homology is like the same. The first homology of open simply connected space also 0, right? Okay, so somehow this cohomology and the homology has relation. Can you see? First homology of star shape also 0 because contractible. Okay, now you use function way to see it also 0. Okay, this is the thing you learn in Cal 2. Okay. Okay, but however, if we make it not contractible, then it is non-zero anymore. Okay, because there's something in the kernel that cannot be written as a graph of something, of the scalar function, for example. Okay, so if your space is not contractible, then this H1 is non-zero. Okay or not? So previously, when you look at homology, right, you are looking at topological space itself. But now we are looking at the function defined on the topological space. You look at function. Okay, function. Function means what? You input your point in topological space, you output maybe something real number, z or whatever. Rings, output into rings or modules. Okay. The space that we can do calculus, for example. Okay. Yeah. So then you can actually define H0 as well. So H0 is just the kernel of gradient. Okay, kernel of gradient. Just now was curl and grad, right? So you can define H0 as the kernel of gradient. So if and you can prove that if an open set is connected, H0 of U is R. So here R is because we define this function taking values in R. So your output is R. Previously, your chain group was defined on Z, so that's why you get Z. So now we define on R, you get R. Okay. So you see, this first homology here has some relation to first homology also, because if your space is connected, what's your zero homology? Number of path connected component. Okay. Yeah. For the detailed calculation, you can have a look. Just I want to tell you there's some facts here so that you can try and link cohomology and homology together. Okay. There's some things for you to check here. You can check yourself. So then we can extend the idea to R3 as well. Okay, well, so in R3, why we consider R3? Because after grad, after curl, we can do diversion. Okay, divergence. Okay, we can do divergence here. Correct or not? Divergence you can do on R3 because you need more direction to go out. Diversion can do in R2 or not? Can? Yeah, should be a. All dimension can. Okay, good. Huh? Sorry? I can only do R3. Just now we did it in R2, right?
That's exactly to just use from action.
Oh, is it?
Yeah. I like
Hmm.
R4 and and in a more generalized definition, but not this one.
Oh, okay, sure. Oh, is it? Okay, yeah. Okay, but anyway, so you also can check that divergent and curl also composed to zero. Okay, so actually these form a chain complex. Yeah, yeah, these form chain complex. So something like that. This one can skip, I think. Yeah, so you can try and read these motivation. So even more general would be these. You can take your real vector space as the differentiable P forms. Yeah. So what are P forms? These are the map from open set to wedge product of Rn. Yeah. Exterior power. And then you can define an operator called exterior derivative. So the previously is the first three exterior derivative. Okay. And then you will define this close and exact. So symplectic case, right? Symplectics, we always talk about closed form because they are considering some element inside this cohomology. Yeah. But anyway, this is just something to let you know what's happening for cohomology theory. But later we will go more into the technical detail. Okay. Right. So what actually are these higher dimensional H cohomology doing? Actually, they are trying to kind of finding anti-derivative. They're kind of finding anti-derivative. So actually, the cohomology will measure how many closed forms that are not exact. Correct or not? Because we call the things inside the kernel is closed form, and then the thing in the image is exact. So if you're D of something, then you are exact. Okay. So this is like kind of finding anti-derivative, correct or not? because just now your function is d of something. So who is the antiderivative? We just teach calculus one this time. For example, d of sine x equals to cos x, right? So cos x is the antiderivative of sine x. 有讲错吗？所以讲错了。Sin x is the antiderivative of cos x. 为什么？ Because if you apply integral on both sides, then you integrate cos, you'll get sine. So sine is the antiderivative. Cos is a derivative of sine. 这样子。OK， 把它讲一下。OK 啊 ，Yeah. So this, so you can think of cohomology like measuring. Can you integrate or not? Can you integrate that function? Finding the antiderivative. 它是一个 algebra 的 structure 来的，你可以去找找看。等一下 ，later we will teach that. Later we will teach exterior algebra. Okay, this one proof can skip, you can read. 需要讲吗？哇，这个是很好的东西，可以 motivate 去做 PDE. So since peoples are built from a local information, so we just look at open set. We can actually put them together to build a theory on a manifold. And then this whole idea is essentially getting at the question whether we can solve PDE or not. Because we want to find the antiderivative. I tell you the derivative already. Can you find the antiderivative? Okay. And then what else should I say? Yeah, so if you have a closed form equal to 0, right, this is like d of something equal to 0. So actually it's a bunch of differential equations. And then finding eta such that d eta equals w will give the local solution of this system. Correct? Because d eta is 0. d is 0. Okay, so your solution could become from some d of something. Okay? Yeah. So that's why there's a whole business of turning this PDE stuff into this cohomology business. And we understand in that form. For example, if you can go and search on something called D modules, this is the business they're doing. D modules. What are D modules? The D stands for these derivative. D modules. Yeah. 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 So is to so related to a problem to find antiderivative in the higher dimension. Yeah. So yeah. For higher dimension. Yeah, because the derivative you did was just in one dimensional, 0 dimension, 1 dimension or 0 dimension. 0 dimension is a 0 form. Yeah. Okay. Right. Another equation is from cell complex. This one I don't want to go through. This one is something in the lecture. But I want to go through something in elementary school. Think of Z100. 1 to 100. How do you add in your elementary school? 1 plus 1 easy lah, 2 plus 3 easy. But how about 6 plus 7? This is the place where people first start. How to add? Cannot. 怎么加到13呢？用手算手翻过来，手用脚指算。Okay. So now we're gonna introduce this using abstract algebra way. We want to even worse. We want to use cohomology way. Even worse. Okay. So first of all, 敬畏这个东西 how to say？ 敬畏的 English 是什么呢？敬畏的 English 是什么？屁了。差不多，好像有一点像 carry over 是比较简单的词是吗？有没有一个比较 technical 就是 carry over 吧？我忘记了，忽然间忘记。不是吧？我记得有一个特定的词。Anyway, so basically, you view it as a coset of 10。
就是 carry。
是 carry over 哈，就 carry over 哈。OK， 好吧 ，carry over。因为我从小都是用英文学，用华语学的。But anyway，so we consider the coset of tens, coset of tens. Okay, so you have a subgroup inside Z100. Your subgroup is 10. You mod Z100 by 10. What do you get? You get 10 cosets as well. Okay, so actually you got two Z10. But it's a different way. One is coset, one is the subgroup, the normal subgroup that you quotient out. Okay, so can you imagine how we're gonna teach you addition in this way? Can you imagine? Can you imagine? Okay, now we really do something very interesting. You look at 53, right? 53, for example, we split the 5 and 3 up. 5 is a coset it lives in. 3 is the element in the subgroup that you quotient out. Okay? Quotient out. Normal subgroup. 3. Okay? Make sense? So meaning the bracket 3 is the equivalent class of 3 inside 10. 5 is a coset. Okay? 5 is a coset. Sorry, let me think. So it's a coset of 5 1. 对吧？我想一下，对啊，没有错啊。50, yeah. Okay. So really, this 5 is 50, 3 is 3. But we just split the digit up. So how do we add? So we define the addition digit by digit. So we split the digit up, and then we define the addition. How to define? What do you think? 你想想看，应该讲讲。直接加的意思是什么？我已经 split out 它的 digit 了，然后你要跟我讲 digit by digit 讲加。OK 哈 ，OK 差不多要到了，差不多。OK, so basically you take A1 plus A2, but there is a function of B1, B2, exactly on the carry order. 怎样讲的 carry over 定位？不是，我不是问的，不是，我一直说怎样 define Z， 我到定位了，我也知道 carry over 对，但是我现在要问的是怎样 define 这个 Z。define 啊，明白 define。对，but anyway， 就是有一个 function 要解决掉这个个位数怎样加就对了。上面那个表，哪个？上面那个表。对，没有错 ，based on 上面那个表 ，OK，based on 上面那个表 ，so 这个表在做什么？看得出来在做什么 ？OK， so well I mean B1 plus B2 你肯定要加罢了的，你加了过后就像Lydia讲的 mod 10， 因为你只要拿它的后面那个位置，但是那个 E 怎么加去 A1 加 A2 呢 ？Using 这个 use the Z B1 B2， so how do you define it? Here, use this， 跟那个3、4、5岁的讲这个 table 另一个 table。然后这个号码对到这个号码有1的话，就1可以来定位的，对吗？不是 ，I mean half of it is 0 makes sense right because it's less than 10 the sum, right? Yeah, so you don't need to plus 1. Okay, but if it is at the lower diagonal, then you need to plus 1 to your the coset part. Okay, but a very interesting thing is this function, okay, this one we define by elements, right? This function actually have to satisfy the associative condition. Okay, associative condition. So if you write down this associative condition, you need to make sure these terms add up to be 0. And then this is what we call a co-cycle condition. Okay, a function that satisfies this condition to be 0, we call it a co-cycle condition. So co-cycle here is like a cycle. So that's the function that evaluates to 0. But this is the way how you evaluate. Okay, last time we were using the edges, right? Edges minus edges become 0. But now here is a function applied on some input and then you combine them. Can you imagine or not? Can relate this to the edges thing? The edges is like plus, remove the first one, minus, remove the second one, plus, remove the first one, minus the second one, equals 0, right? But now this is a very similar thing to do. You have a thing inside a kernel that evaluate this, minus evaluate this, plus evaluate this, minus evaluate this. Can you understand or not? Imagine inside here is the edges. Cycle case also you need to do that one, right? For example, why a loop is a cycle? Because the starting point and the ending point is the same, so V minus V. So here is like V minus V plus V minus V like that. So this is the core cycle condition because we consider function instead of points on top of each other. Understand? Okay. Yeah. Okay. So the function on carry over actually is a core cycle. It's a core cycle. There is an element inside the homology. Cohomology. OK 哈，几岁啊？现在几岁啊？几岁？3岁，20岁啊！看到加法不要这样，是不是？这个人生没有白活，对不对？你这样子吧，你给他看这个 table，遇到了才给我敬畏哈。OK， yeah. I mean, another way is you can think of it like an inner product, right? Inner product. I mean, like inner product between the element on the horizontal and vertical column, the first horizontal and the first vertical. Okay. Yeah, and then there's another condition you can check on the identity. This is what they call a normalization condition. Yeah. Anyway, so these are the motivation for it. Yeah. So I'm trying to convince you that cohomology is kind of useful. Then we will go into the technical part. Okay, so we'll go into the technical part. Yeah. So let's see. What time is it? Should we take a break? Any question? Any question you want to ask before we start later? Before we finish, I also have something to say from last time. So last time we didn't say clearly what's the natural transformation, right? Let me draw something. So we introduce you category of top. Okay, so top logical space. Okay, and then inside the top you have a topological space. What do we label XY? What is the usual terms we use? XY here maybe. Then inside this category we should have a map, right? F to Y. Okay. Then we go from top to let's say com of Z, chain complex of Z. So we have like Cn, C bullet and X, and then C bullet and Y like that. Okay, and then if you give me a map between topological space, we also will have a chain map between vector space. Sorry, the chain complex. So here we put F's induced, right? Induced F. So this is given by some functor F. Okay. For example, one kind of functor is singular, not singular, CW complex or cell complex, right? And then singular simplex. These are the possible way to go around here. So example of functor here we look at was cellular chain or singular simplicial chain or singular chain. What else? That's it, right? Anything else I missed? Singular. Yeah. Okay. Then what? Then there's another level of map that I didn't tell you. So for example, last time we showed that, let's call this a different one. So we show that cellular and singular is the same, right? So let's call this G different one. Okay, so if we want to show that these two are the same, actually we need a map between them, singular, a map between them. And then the map between functor is what we call a natural transformation. Okay, so natural transformation here also need to satisfy some naturality property also, meaning if you have function between two terms of functor, then how do you map between natural transformation? So for example, this here, okay. So let's say you have map between natural functor. So if let's say you have map between the objects, how do you transfer the map between natural transformation? So you can apply your functor to this f so that you get this two vertical arrow, and then you need to make sure that this commute. Okay, so this is the extra probability your natural transformation need to satisfy. Okay, so if you look at category, the definition of category, all the maps or the category itself have to come with two pieces of condition. One is how do you treat your object? Second is how do you treat your function? Okay, so treating object is just send the thing to another thing in that different world, but function is very different. There's some commutativity property you need to catch because they want to build this theory consistently. Okay. Yeah. So there's a very prominent figure in category theory, in particular infinity category. The audio option, like me. Okay. So one of the connecting homomorphism, transformation, natural transformation you see is this boundary map. Okay, boundary map. The connecting homomorphism, connecting homomorphism. Okay. If you still remember last time we showed some functoriality on this homomorphism, connecting homomorphism. Shall I show you? I think it's better I show you. So this square property here will suggest there's a natural transformation between them. So connecting. I think I didn't prove it with you, but it was stated here. See, it is. Okay. If you have function, if you have a morphism in between this two term here, then this natural transformation will come. Okay. Yeah, so it's a natural transformation. Okay, so in this class, technically you already see category, you have seen functor, you have seen natural transformation. You are secretly already seeing them, using them, computing with them, calculate with them. Okay, yeah, but if it doesn't make sense for now, it's okay. In future, it will make sense to you. Okay, so we can start using this language to talk about them. Okay, we can use this language to talk about. Okay, so far, any question, no? Before we take a break. Any question? Okay, so what's cohomology? Please, what's cohomology? Okay. One of the application. So another thing I think I want you to remember is homology is about topological space. Cohomology is about function on the topological space. This is very important. And this is very important. A bit like algebraic geometry. What is algebraic geometry actually? It's studying the algebraic varieties and the function defined on the algebraic variety. Coordinate function. Yes. In that class, both of them are important and both of them are important. Okay. So in this class also, you will learn homology and cohomology. One is topological space, one is function on topological space. This is where the contravariant and covariant thing come up. So if you have map in between topological space, then on the homology level, it is a covariant functor because when you induce the map, the order is the same. But if you remember in algebraic geometry, right, we induce the map on the function, it will change the order, become contravariant. Later, you will see the same case in cohomology because the object we consider is home from the topological space to somewhere else. For example, real number, for example, Z. Then everything goes to the same space. So it's a function of that space. Okay. Does it matter? Is it clear? So one thing is I want to understand what is this. This is the method. But then we want to measure, okay, how many ingredient, I mean, what's the percentage of this ingredient? So ingredient is this medicine itself, but I can turn it into percentage. Right? But also important, right? Because this percentage more than that percentage, then this have maybe become a drug. It's not a medicine anymore. Okay? Both things is very important for this to be useful. Okay. Okay. Yeah. Okay, so we will resume again.啊？为什么？什么？嗯，function from homology，function from homology 哈，非常好。等一下就是我们要做的事情。我们为了 study cohomology，我们可以 relate back 去 cohomology 的 function，homology 的 function。对，等一下我们就要做这个事情。这个就是那个姚一成想知道的 extension 的东西。X homology 跟 function from cohomology，sorry，cohomology 和 function from homology 相差的是一个 x，一个东西叫做 x 啊，等下会看到。我们等下就是这样子去 study cohomology，relate 去 homology，instead of 从头算啊，但是也可以从头算啊，也可以从头算。没有错啊，问的问题越来越在线上了，很好啊，线上，I mean like，对啊，就线上就来在，就是问对的 direction，想的方向对啊， 路亚。嗯，
拼后跟游戏有什么差别？
不一样的东西啊。Actual derivative 是一个 operation 来的，K form 是一个 function。Actual derivative 是从 K 加呀，对，没有错，它是一个 actual derivative 是一个 function 来的。OK，到一个 function on K form，这样 K form 自己是一个 function，但是那个 function 是从 open set 去到刚才讲的那个 exterior space exterior，这里不是号码诶，那个东西是一个 algebra。
拼后不是一个号码？
嗯，Well, I mean，如果你是 consider zero form 的话，还是去一个号码啊，但是 one form 好像就不会。哪一个 form 啊？One form 是去号码吧，two form 就是去号码。哦，好像是哈、
都是这样。
哦，是哦。那刚才我那个 definition 在写什么？
exterior derivative 和 k 空，
嗯哼，
两个人力两次也是等于零。
没有 exterior derivative 是在指那个 operator itself 那个 partial 那个 partial，那个 form 是 d 什么东西的吧？我
都是里
看写
面的东西。
什么 d 哪个里面？
你那银刚写的
D on 那个 form 过后就变成 form 了啊。SU derivative 是在指那个 D 本身啊
太多。
啊，对，没有错。怎么我这样子写那个定义呢？给我看看，smooth maps from U 去这个地方，
就是有
我有 define 错吗？哎，可是 P form 是从 U 去 R，你是说check 一下这个 definition 的写法有问题吗？或者说这个 wish 了过后是一个号码啊？let me think。我觉得这个应该是 definition 写法的问题吧，I think，但是要怎么去理解它是一个问题，Yeah，I guess 怎么说诶？因为它这里的意思应该是说你的 W 可以写成 D of 可能 D of E of 可能 XI，sorry，D of D of 啊、D of I E X I E 这样，然后 wedge 到 D of I P X I P，然后每一个啊，是吗？是这样吗？
因为它的 image
？Image 还是它的 P form？
的 assignment，因为你要 differential 做 p form，所以你 assignment 是 smooth 的。
是 smooth，因为通常是不是只能够 define 在点上面啊？每一个点上面的 form，我们是不是要 define 在点上面？因为这里有好几个 input 呀，对吧？
呃，
我觉得它这个 input 是点吧，你一个点上面就装这个东西，另外一个点装这个，另外一个点装这个，然后你装的时候要 continuous，要 smooth。
W 是啊，
嗯哼，嗯哼，
你的 p form 是后面那个。
它应该要整体都叫 P form 整体。 整体。就比如说你写 dx 的时候啊，你不能够说我在1是 dx，在0不是 dx 呢？你不是整条都是 dx 呢？是这个意思吗？对吧？你在整条 real line 上面都是 dx 啊，你的 integral 又不会来从这一段到这一段是用 dx，从下一段用 d2x 什么这样，对吧？所以这个有一点像那个 canonical 的东西嘛，对不对？canonical divisor 就是这个东西啊，就在讲这个 canonical divisor，就在讲这个，就是有一个 x 可以有一个 ds 可以放在每一个点上面，canonical。为啥？这个是有一个 algebraic structure 在上面的，它是一个 algebraic structure，就是比如说 dx wedge dy 等于减 dy wedge dx 这样，你转的时候要有一个符号，说这个会 imply dx wedge dx 等于零，其实等一下我们会介绍这个东西叫 exterior algebra。x 是什么？wedge wedge wedge 啊 wedge 是吗？那个boundary map 想一下，assign orientation 放一边有没有关系是吗？对啊，你说这个0去1啊，然后哦哦，没有，不是那个，中文呢？中文你讲关系的呢？没有吧？没有。它这个纯粹就是说我把两个东西相乘，它是一个 anti-commutative，是叫 anti-commutative 的关系吧？然后这个 anti-commutative 就可以 prove that 你如果 wedge 同一个东西在一起，它会拿到零，因为你翻来翻去是同一个东西嘛，但是它是相差一个简易。Yeah. Okay, but we will talk about this wedge again. Okay, so where should we continue then? Where should we? Yes. 这么不可以？谁要讲就去讲啊，share 一下自己的看法。Okay, so let's continue. So we're gonna do cohomology, huh? But we will start with homology first. So let's say we have a chain complex. Let's just talk about free abelian group first. Later we'll upgrade everything to R module, okay? Because we're gonna use some tools from R module. So let's look at the usual one. Okay. So now is the down the subscript version. And then this is a decreasing version, n plus 1 to n minus 1 because it's the n cell. N cell to glue to n minus 1 cell. This is how you should remember. Okay. But let's say we have a abelian group, any abelian group. Then we will apply this, let me use category terms here. The contravariant functor. Okay, contravariant functor. So what's this functor? This is a home functor here. Okay, because you should imagine that this home is another group or another module again. Okay, so that's why it's a functor between chain complex to another. Haven't tell you yet. It's again a chain complex of this G module or Z module here, Z module here, Z module. Okay, so what's this thing here? So basically, you just write down the chain group, and then you write down this element here formed from this chain group to G. So far, make sense or not? I just consider maps up from the chain group to G. Okay, but now how do I put the arrow? What do you think? What do you think? What the arrow should be? Should I go from C minus one, home from C minus one to home from Cn, or home from Cn to home from Cn minus one? Which direction makes sense based on this arrow? Okay, sure. I tell you the answer already, but before I tell you answer, can you think why is it contravariant? Okay, very good. I tell you contravariant. That means I need to go the other way, right? But like, why is it called contravariant in this case? Okay, so go the other way, meaning you go increasing, just now decreasing, now you go increasing. So now my question is, why is it contravariant? So let's say you take element from Cn minus 1 to G, right? Okay. And then you have a map from where? Out of Cn minus 1 or into Cn minus 1? Which map you have? You have into, right? Delta n. So meaning what? You can compose, pre-compose, right? You can pre-compose with your Cn minus 1. And then these all together will become a map from where to where? From Cn to G. Okay, so you produce a map from Cn to G. Does it make sense or not? Can you understand what I say? Okay. So meaning what? If you have a function, let's say n minus 1 cell, that evaluate on s minus 1 cell, you can let it evaluate on the n cell. How? Just look at the boundary of your n cell. Turns out that very useful. Okay. You understand what I say? Previously, we are taking n cell to n minus 1 cell, right? You need to look at how the n cell grew to the n minus 1 cell. But in that case, we also only consider their boundary, right? Because the n minus 1 cell is living on the boundary. But here, also the same one. We take the function that can evaluate on n minus 1 cell, let it evaluate on n cell. But we are not looking at the whole n cell. We look at the boundary of the n cell. Make sense? Make sense or not? Okay. Yeah. 什么？看它 boundary can expand 已经没有，就是纯粹 evaluate on the boundary of n cell. But if your action is on n cell, but you only checking on boundary, you don't need to check everything. You just check on boundary. Because the boundary of the n cell become n minus 1 cell, so you can apply your function that add on n minus 1 cell. OK 吗 ？OK， 可以吗？明白吗？kawan sekalian. Okay, understand? So then this is what we call the co-chain group. Co-chain group. So these are the co-chain group. Okay. So co-chain group is C to the N, defined to be the Cn dual, which is the form from Cn to G. Okay. Everyone okay with me writing Z at the bottom here? This Z just says that this is the scalar in this space here. Okay, this is the scalar here. Okay, so far any questions so far? All good? Okay, so change direction. Is it changing direction now? This is like if you take algebraic geometry before, right? The coordinate function is a function that from algebraic variety to real number, for example. Okay, so you also have this induced map change. Okay, in that case, how about the boundary map? How about the boundary map? So this is our boundary map. This is the boundary map. So delta here. So where is the delta? So this is the delta. And then delta is defined to be this. Okay, delta on F. So what is delta F? So go and do your boundary map on your N cell first, and then only you evaluate F. This is the boundary map. Do you want to check this is composed to 0 or not? You believe, or you want to check delta 1? So here is delta 1, here is delta 2, for example. So delta 2 on delta 1 on F. Okay, what is it? So you do your boundary map, right? And then you do again your boundary map. So how should you write down the boundary map? Supposing like this. Okay. You do twice, becomes 0. Can you see the order change here? This one do delta 1 first, this one do delta 2, but this one do 2 first and do 1. And this change precisely there's something to do with the arrow change. Okay, any questions so far? 有问题吗？ Okay. If no question, then since we have this del square equals 0, we can immediately define the cohomology of this chain here. Here we can define it to be the kernel coming from n to cn minus 1, proportional by the image coming from cn minus 1 to cn, like that. Okay, so we will call this n cocycle and the n co-boundary. So previously we have cycle and boundary, now we add a core to it. So adding a core meaning you turn the arrow around. Algebra, co-algebra. Yeah. Okay, so far any question or not? Okay, if no question, let's look at some examples. Okay, maybe some examples will be helpful for you. Okay, first example is let's look at this chain complex. So chain complex is decreasing. Higher cell go to a lower cell. You need to glue them. And we look at this special chain complex here. 0, 0. A very easy one. But the middle is a non-trivial one. 1 to 0, 1, 0, 2. Can we quickly compute what is H1, H0, H1, and H3 or not? Can you quickly compute? H0 is what? Where's the H0? So here is D3, D2, D1, D0. So D0 is 0. Okay, so the kernel is everything. D1? D1 is a 0 map. Also, kernel is everything, but image is different. No? Image is generated by the element 0, 2. Okay, so meaning what? This is isomorphic to Z and Z2. Okay, H2, kernel of this map multiplied by image of this map. So what's this kernel here? What map is this? Is this an injective map? Okay, this is an injective map because you have a pivot in every row, so it's injective. Okay, so the kernel is 0. Ali is at the opposite side. I can call Ali here. Ali just next door only. Ask Ali to explain why is this injective. Okay, H3. H3 is a 0 map. Image is nothing, so is that. Okay, so this is H0, H1, and H3. But then if we consider the core chain, what happens? Okay, if we consider the core chain, what happens here? Okay. So instead of changing arrow, now I change this order, increasing order. Okay, so we just write everything down. So one is from Z to Z, and then from Z plus Z to Z, and then a home from Z to Z, and then home from Z to Z. Okay, so now I think there's one technical thing you need to realize here. So what is home Z to Z? How do you categorize home Z to Z? So what's the homomorphism from Z to Z? What do you need to know? What do I need to tell you to define a homomorphism here? Z is a, okay, if you know it is a principal ideal domain. Another thing is it is generated by one element. So meaning you just tell me where one go, you should know where everything go. But how many choices you can have? How many choices? One can go to any end. So you got like all the maps determined by where you want to go. So meaning what? Actually, this is just Z, isomorphic to Z. Okay, because this isomorphism is you know where you want your function that sends one to n, then the homomorphism is just sending that function to the element n. You can show that this is an isomorphism. Okay. Similarly for Z plus Z to Z is the same. You just need to tell me where the 2, 1 can go. There are two generators here, right? Where are these 1, 0 and 0, 1 can go? Okay. They can go to potentially different things. Okay, so this will give you a isomorphism to Z plus Z. Okay. So what did you observe here? It seems like quite easy, huh? You just pick their domain and it will become the space that you are interested with. Okay, this is the case for this kind of what do we call it? Projective modules. But we didn't introduce what the term is. Just want to tell you that there's some special property that makes this true. Okay, then we need to figure out what's this boundary map now. Okay, you still remember what's the boundary map that we imposed on them just now? You still remember? If you take the f here, okay, what is delta 1 of f? Okay, you need to do the boundary map first, right? Okay, so what's the boundary map in our case here? This boundary map is 0 from z plus z to z. So if you evaluating everything to 0, because this is a homomorphism, so it must send 0 to 0. Okay, so this is f on the 0 map, which is 0. Okay, next level. How about a function from z plus z to z? This boundary map is different already, right? You're gonna send 1 to 0, 2. Okay, you're gonna send 1 to 0, 2. What does this mean? What does this mean? If you have a function, so let's say if you have a function here, okay, what you're gonna do? You're gonna send f to f of a and to b like that. Correct or not? Sorry, from a f of 0 and then to b. Correct or not? Yeah. 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 Okay. So how about next level? Next level is again 0 map. So this is a 0 map. Okay. But after apply the homomorphism, what happens here? Okay, after you just, if you don't look at it as a function, you just look at it as an image. So you can trace to this isomorphism here. So n will go to a function that sends 1 to n, and then go through this boundary map, and then send back your image of your generator. What do you get? You're going to send to 0 already, right? So 0 under this map, under this isomorphism, the function that sends things to 0, you also get 0 here. This is a function that can send to 0. The image also 0. Okay, but how about this? This is a non-trivial thing. Okay, so if you start with nm, you go to a function that sends 1, 0 to n, 1, 0, 1 to m, and then you go to a function that sends n to 0, and then m to 2m. Okay, and then you come back again using this isomorphism. Then what you get is you're gonna send AB in this case, or NM, maybe use NM to 2M because the N part disappear. Okay, and then the other one is 0. Okay, so this is the new chain group now. This is the new chain. Okay, so this is the new chain. Can you compute what is hash 0? What is hash 1? What is hash 2? What is hash 3 or not? Okay, so hash 0 is what? Is a 0 map. And then image is 0. Okay, these two arrow is important. So this is Z. Hash 1 eh? So what's the kernel of this 2M here? What's the kernel of this map? 2M, NM to 2M. Who is in the kernel? So the kernel here is the A, right? Only the terms A gets set to 0. So it's generated by A0. Okay. And then what's the image? Image is 0. So it's just isomorphic to Z. Okay. So this spot, the free variable appears here. Okay. I mean, if you want me to write down the matrix map is I think you need to write in this way. 0 and wait, let me think. Should I write in this way? So your NM is like that. And then this is 1 to 2, 2 times 1. Okay. So 0 and 2M, like that. Okay, so what's in the kernel? One free variable. Okay. H2 eh? H2 is this 2 map here. So kernel is everything because 0 map. So it's Z. And then image, image is 2Z. Okay. So this is Z mod 2. H3 then is Z. What can you see here? What can you see here? Can you see anything? Lydia? Can you see? Can you compare homology and cohomology? It's the same group, but order change. Can you see order change or not? Homology, the Z2, different group as well. Different group actually. Different group. So H0 is Z is the same. H1 is Z plus Z2, but cohomology, first cohomology is Z. And then H2 is 0 on one case, the other is Z mod 2. And then H3 is the same. Okay? Can see? So kind of like H1, the first homology, like steal the H2 homology. Like that. Can see now. So there are 3 integer and then 1 Z2, right? Okay. Yeah. Okay. There are some relation, kind of have some relation. Then later I'll tell you what's the exact relation between them. Okay. Same group have appearing, but in different spot. Like both of them got 3 integer and then 1 Z2. Okay. Actually, they are very precise relation, which we call the universal coefficient here. Yeah, later we'll see. There are examples, other examples. I don't want to compute with you again. You can check the notes. So for example, after computation, maybe I can show you this. That if you look at this is part of the RPN, right? 0, 2, 0 of the alternating boundary map 0 and multiply by 2. This is like RP, how many are this one? RP3. Okay, RP3, chain group of RP3. Then you look at the map from RP3 to Z again. Okay. And actually it's the same chain group you can compute. Also 0, 2, 0. Okay, and then you can compute that HN theta and HN theta here. What can you see? What can you see? The top, the first and the last is the same, but middle swap. This is not a coincidence. Okay, in the last part, maybe next week, last day, no, 2 more weeks, last day, I'll show you something called a point correct model. Exactly talking about this swap. Okay, not a coincidence. It's not considered. Okay. Sure. Please go back and check my calculation. Okay. So since the co-chain complex is obtained from the chain complex by applying a functor component-wise, we will show that the cohomology groups are actually determined solely by G and the homology groups. Okay. So because we are just applying the hom, right? Okay. So hom, what is inside the hom is just where you send your chain group to. So that group is important. That group G is important. Another important thing is the homology. Like just now Jinsen will ask, can we just compute from consider the map from homology or not? Yes, can. So this is the two things that determine your cohomology. Okay. Okay, no? Okay, so we will do this step by step. Okay. First thing we want to do is there's a surjective natural map from the N cohomology to the home space from the N homology to G. Okay. So there's a surjective map. Should we do this? Feel like don't want to do. Can you accept this?
Yeah.
As a, okay. So the point here, if I told you surjective already, what's the next thing you should think about? We are interested in what subjective map always. Kernel, yes, good. So we want to figure out what's the kernel. Kernel with this form will build your cohomology. This proof is also kind of like a diagram change. You can try and figure out yourself and then check whether my proof okay or not. Okay. And then if you believe these, then we need to go into a crash course on modules. Okay. Maybe again, I need to build a section on crash course on this because I just copy paste random notes inside here. We need to use some result, but we won't touch it. Okay. So first thing we need to define what is R module. So R module is just a vector space. Then we replace your vectors, the coefficient of your vector space with a ring, then become R module. R homomorphism, so it's a homomorphism between groups, but now you got a scalar, so you need to tell me how the scalar react with your homomorphism. So basically, you can pull the scalar out. That's it. Okay, and then another thing is we want to talk about this a bit of homological algebra. So it's not hard to check actually. So let's say if you go one-sided exactness like this, one-sided meaning you exact one-sided go to 0 on R module. Because if you apply the home functor, right, the arrow will turn around. So go from A prime prime to home of A and then home of R, A prime. Then this new chain complex here will be exact on the left with 0. Left exactness. So it is left exact. Okay, so meaning if you apply it to maybe let's tell you why we call it left exact. So for example, because maybe you want to apply it to some short exact sequence, right? So it won't be the case that the other side of exactness get preserved. Okay, only one side, which is just left side. So far, any question? Understand or not? I didn't expect you to prove yet. You understand what I say first? Okay. Okay. So proving this is a diagram chess, so let's not do it. You can go and do. Yeah, just showing the kernel equal this. Actually, is it possible to give this to the second year to do? Huh? Am I kidding? Yeah, I mean, can I hide it into like ring stuff? There's nothing much, right? It's just showing image equal kernel using X. 啊，对，猜一部分，但是要假猜啊，又可以用一些那种加根。 ，exactness 呢？要介绍 exactness。OK，yeah，OK，哦，放在 assignment 哦，assignment 可以，OK，好，so 嘞，我们上次那个第三题我忘记了，我可以看一下，可以考虑一下。Yeah. Okay. Next lemma is just now. If you don't have split, you don't preserve the whole exactness. But if you have a split exact sequence, so meaning you can write A equals to A prime plus A prime prime, then this whole functor will be splitting as well. Okay. It preserves split exactness, but not exactness. Yeah. Split 就是写成 direct sum 那个 there's a section going from A prime prime to A, or there's a section from A to A prime. Or you can write A as A prime plus A prime prime. This is split. Split. Split exact is exact. Split exact is exact plus split. If your short exact sequence is not split, then you're left exact. If it's split exact, then the new chain complex is also split exact. So you got two sides, exact plus split plus split. Okay, left right exact plus split. 就多两个东西，其实不止一个东西。Okay, also don't want to prove. 很任性啊。Okay, next is same thing that you got from homology. So if you have split exact sequence of chain complex, then you will have a long exact sequence on cohomology. Okay. Okay. And then next thing is about free. Okay, why we want free? You should think of Rn. Rn is free. Rn is very free. This is the first free thing you see. Sorry? 什么 theory? 用书放的。Okay. So it's free meaning what? You can write it as a direct sum of the one-dimensional module. Okay. So one-dimensional module. So one-dimensional module here correspond to the module generated by your basis. Yeah. We call basis here. Yeah, we call basis. So the prototype you should remember here is Rn. Again, Rn. How do you build Rn? So the prototype you have to remember here. This is something called free prototype. Prototype. So Rn is free because we can write Rn as a direct sum of R n times. 是这样写吗？不对哦。n 次要这样写。I equals to 1 to n. Or you should think of it is as R times maybe your standard basis, your favorite standard basis. Okay. Okay, next thing, wow, this one very technical. Let me see how do I motivate you. Let me see first. Okay. Okay, we'll call something a free resolution. Okay, so what's the free resolution? 不要忘记这个字，忘记这个字先，忘记这个字。Okay, you just take exact sequence，就这样。Exact sequence of what? Exact sequence of free module. 什么意思？ So inside every terms inside your sequence is an R module, free R module. That's it. Okay. And then free R module, what this module do? It has to connect to your M at the end. That's it. 就这样。And M 可以不 free. M is an R module. So you can think of it like this M module may be not free, but I want to estimate this M. How free is it? So I put another free module, send to M subjective mark, accept mark, subjective first, and then I look at the kernel, and then I inject a free module into the kernel, and then 又有 kernel 再 inject， 又有 kernel 再 inject， 又有 kernel 再 inject。That's how you got this exact sequence of free module. Understand 吗？我在讲吗？
要不要给
？OK， 我觉得你问的问题很对，但是我现在想得出吗？我想不出一个 non-trivial，应该我要懂这个东西，但是我现在没有记录的。有一个 non-trivial 的，让你可以一直做。I mean like 很简单的 case is like R module，then 你就放一个 R 就好了嘛，它就断了，因为你可以放 identity。OK，non-trivial 啊，let me think。non-trivial 想一下 non-trivial 啊，yeah，什么 kernel？因为 kernel 等于 image 嘛，so 不一定呀，不一定呀，不一定。如果 inject 的话，我就可以断掉它呀，不一定。让我想一下，is Z mod 2 a Z module 啊？对，Z mod 2。如果 let's say Z mod Z mod 2，and then 我可以放一个 Z here right，and then here is a times 2够吗？不够，这个是一个 Z mod 2的 map basically is just mod 2，and then what's the kernel here? Maybe 2 咯，right? 2 times Z is in the kernel. But what's the kernel here? Then 这个就会断了。我记得有一个 very classic 的 example 是不会断的，我现在想不起来。呀，我应该要懂这个，但是我忘记了。你可以问一下 ChatGPT。有一个最简单的 example，它是不会断的。OK，so far OK 了。Free resolution of an R module, meaning you're trying to use a free module to approximate this. So you put a bunch of free module inside of the sequence. OK 吗？不要被这个字吓到啊 ！resolution，重点是那个 exact sequence of free module，把 exact sequence of free module 放在 M 的后面。好吧，是不是 ？OK，我不用 remark 这些了，这些 remark 不重要，到你要算的时候，你就知道它很重要。OK，还是要讲一下吗？不要讲，算了，慢一点，遇到我再讲。OK，so then we can define what's called the X module here. Okay, so what's X module here? So X module here, you need to consider two modules. One module is M, one module is N. Okay, so what's this M and N doing here? So N here is the use for your home. Okay, home from your chain complex to N. But what's the chain complex we consider here? Exactly coming from M. So how a R module will give you a chain complex using this free resolution? Okay, a bit like topology case, right? Topology, how do you create a chain complex? You got a few ways. You can use cellular, you can use singular, you can use simplicial. Okay, but in this case, we use free resolution. I give you an M, go and take one free resolution. So now you got question already, right? So many resolution, which one I should take? Then this one come with this lemma here. This lemma here. If you take any two free resolution, if there's a map between these two resolution, then it can extend to every terms. Okay, and then any free resolution, any two free resolution of M will have a canonical isomorphism between their cohomology. So 你选哪个问题？他们算出来的 cohomology 是 isomorphic。OK，可以吗？没有问题啊，随便你选的 free resolution。OK，帮你解决掉第一个问题啊。说这些 proof 啊，这 proof 好非常 homological algebra。Anyway。So what's S module here? What's S module? 听清楚啊 ，What's S module here? What's S module here? 有意思。What's S module here? 看清楚。So you take a M, you take a free resolution, exact sequence of free module that ends at M, and then you look at the chain group, apply this contravariant factor, then you will get a cohomology or core chain. After core chain, you take cohomology. And then these cohomology are the X group.
C star.
C star is the free resolution of an exact sequence. You need a chain, first chain complex. So they can apply this contravariant factor.
N is another one.
N is another module, like the Z we consider this now. Okay, so the cohomology of the free resolution is the X.
Free resolution is, I think free resolution is always.
Yeah. Free resolution is exact, but like what we said just now, home only preserves left exact. So your anything beyond that, yeah. Okay, it's only exact at this part here. Yeah. So only this first three term is exact. Beyond that, not exact anymore. So there's a non-trivial thing coming up. Okay, first three term exact away. If I continue this exact sequence, then those cohomology could be non-trivial already, because you only have 1, 2, 3 term exact. Okay, make sense? So that's why 那个书从后面的 x 开始讲。Okay, right，还有什么东西要讲呢？3.47，今天应该还是 prove 不到那个 universal coefficient theorem 的。But let me see what else worth to say. Or maybe we can state it at least. Okay, so let's look at some example. For example, this example. Okay, so if M is a free module, so what's the free resolution we can take? It's already free, right? Then we just take another free R module. Okay, this is the free resolution. Then you can compute what's the X. What's the X here? Then what's the X here? Well, I mean, like to compute X, you obviously need to compute the home first, right? The home function applied to this. But I think there's one thing that you need to keep in your mind is what is home M to M. This is something that you need to know, I guess. Okay. What is home M to M? You need to know. What's home M to M? So that's why we need a crash course. Let's see where did I put the crash course? Let's see what theorem or not. 对，之后会看到。Let me see. This crash course got. This crash course don't have. This one only finitely generated. Okay, so can we figure out on the spot or not? What is the home M to M? I think my claim is just M. Okay, it's just M. Because M is free, right? It's written into direct sum basis, and then you tell me where these bases can go, and what's the possible cases in can go. All the每一个的，不一定要自己是自己吗？可以算吗？可以scalar multiple 吗 ？But they are up to scalar. One more yes. Yeah.
不一定有什么，不一定，handle 自己去自己，
因为你可以全部去领嘛，这样，或者全部去一个地方，okay. Not inject, not subjective. Okay, but anyway, so I guess the induced one you should check out. I think it's also identity. You should check, but it's identity. Okay, this induced map will induce identity here.
相信嘛，check 一下，你检查一下，should be identity. Okay. Because you take a map here, here is M to M, and then you pre-compose with identity 不是又是同一个 map 吗？对 identity map 同一个 function 去到同一个
Okay, then your xmn is 0. 这个 x 的意思是 first x 啊，你明白我讲吗？这个 x is x1，OK，s0 它写成 home 啊，OK，s0 is home。因为可能你去算一下，它就是 home，because 因为它是 exact 嘛，对不对？Exact means what? Kernel equals to image, right? So x0 is what? S0 kernel equal to image 0, so it's the everything here. Okay, and then the next one, kernel of this map equal to the image of this map. Okay, but what's the image of this map? So why is it this term here is wait, let me see. Let me check properly. S0. Oh, I guess. Let me see. Oh, right. I think there's something that I missing for you. Okay, never mind. I think we will start here again. I think there's something I skipped. Okay, we'll start with x again, and then one thing is we want to establish this. Okay, so what is in the kernel of this map is exactly the x term from hn minus 1 of C star. So what's C star here? The C star here is the chain complex of three modules that you get in your cohomology. Okay. So just now we use the free resolution. Why? Why do we use the free resolution? Because we want to define what is x. We want to define what is x. So x. So as long as you have a, let me think. So yeah, extension. So okay. Can you imagine what this short access sequence is? This is a ladder. This is a ladder. So meaning you have chain complex in each term here, right? And then every layer become a short access sequence. Is this what I say? I want to say. Let me think. Let me check. I think I need to draw it for you next time. Okay, I will draw it for you next time. Okay, so next time we will do this UCT, and then we'll talk about what's X on these module, apply what happens, and then this one not very important yet. Then we'll go to cohomology of space. And then from here, we will skip a lot of discussion. Just saying that we can swap direction, then we can get reduced cohomology, and then we can get relative cohomology, and then we can get long access sequence, and then we can get or induce homomorphism, and then on pairs, on relative, on pairs, everything 啊。我不会进，我自己讲吧。说你们最好看一看 addition，OK，、就是画一个箭头，我们全部都可以用。Yeah，OK，simplicial homology。simplicial homology is home from simplicial chain group to G, and then cellular homology, and then cellular 是最后一个我们讲的东西。哦，没有 Vittorius， 这个才是我们最后一个讲的东西。So we will stop here. Only then we will start with fun part of this homology, which is OK。前面那些我全部不会讲啊，我只是跟你讲有这个东西吧。我已经解释完在那个 note 里面了，所以你们最好给我读一下。没有，下一节课会从 UCT 开始讲，然后我们 skip 完全，我会介绍那个讲 build homology of space，skip 完全部你可以做的事情啊，就是全部你 homology 做到的事情 homology 也做得到，然后我们再花时间再 cover 的 ，OK。把我有写那些 proof 在里面，说你们可以看一下。如果有问题的话，我们可以讨论。谁啊？这个礼拜第7是什么 week 啊？第7是谁打那个 no？他。